We were examining circuit analysis in S domain. What we have done up to now, we examined how Kirchhoff current law and voltage law equations will change in S domain. And then we define the S domain definition relation of all the elements that we have seen in time domain. So we call the title is circuit in S domain. And then we said how we can get benefit from the serial parallel connections in S domain. You might remember there are some advantages in S domain that we could use these serial parallel connections, which is not available in time domain. And then we also mentioned source transformation, how we can get this, how we can get benefit from that source transformation in the analysis, also be examined in here. The next stage is this new stage. The title is General Analysis Techniques. Why it is General Analysis Techniques? Because in these analysis techniques, we will be finding all the elements, current and voltages. There are three methods that we use. One of them is the classical method. That means the number of equations to any equations will be written. The unknowns are also to any, so we can find a unique solution. That is the classical method. Now we will be writing less number equations, which are called node voltage method. We are going to write node voltage equations. So this is in this video we will be examining this method. The next one is going to be mesh current method. These two methods will be reducing the number of equations that we are going to write. The next analysis method is going to be a special analysis method. In this special one, we will be finding out one of the elements, current and voltages, not all of them. So this general method, we find all of them. So now let's move to open circuit, see how we are going to examine this method. Open board, and then open board. Here we are. So what we have, that is the circuit that we are going to analyze. We are going to see this method on an example, so you could use the same steps that we are going to use in this one for any linear circuit that you have. So this is time domain. Given a circuit in time domain, there is one dependent source in it. So we've got to transfer this time domain circuit to S domain. How we are going to transfer it? We are going to put the element impedances on it. So in time domain there are element parameters on it. So 100 millihenry, 100 microfarad are the parameters of these elements. But in this side we are going to write the impedances on it, not the admittances but the impedances. So let's do this now. What is the impedance of an inductor? VL, let's make it black. VL is SL OL. S domain definition relation of the inductor element. So L is 100 millihenry, 100 milli 10 to the power minus 3 gives you 0.1. So what is the impedance is 0.1s. So this is written here. If you use the definition relation of the capacitor in S domain, is going to be VC is equal 1 over SC IC. So from this C is 100 microfarad. 100 micro is 10 to the power minus 6 is 10 to the power minus 4. 1 over C that is this one. 1 over C is 10 to the power 4. So 10 to the power 4 divided to S, 10 to the power 4 divided to S is the impedance of this element. That is the impedance. So that is the impedance of this element written here. So the impedance of the in time domain resistant values is the impedance in the S domain. So 10 ohm is the impedance of the resistor, 20 ohm is the impedance of this resistor, and 50 ohm is the impedance of this resistor. Definition relation of the dependent sources do not change like the resistors, so exactly written here. So what is left is independent voltage source. Independent voltage source voltage is equal to this one. So we've got to transfer this function to S domain. When you do the transformation, you can get this. So this is time domain and this is S domain. So this is the circuit in S domain now. So how are you going to write this? There is going to be a list which is given to you in the exam. In this list, you could see the cosine function S domain correspondence is this. So from that list you can write down. Next step is to do the analysis. The analysis method that we're going to use is the node voltage method. We know that. But if you examine here, this is the first node, that's the second, that's the third one. The fourth node is here, but not seen. We remove that. We are not considered this node. Why is that? Because we are saying this capacitor is connected in serial with that resistor. So I can replace those two elements, serially connected elements, with one impedance. What is this impedance? This impedance is Z equivalent impedance is the summation of those two impedances. So Z equivalent is equal 50 plus 10 to the power 4 over S. So this is Z equivalent. What does this mean? This means if you take these two serially connected elements off and put that impedance in, Z equivalent impedance, between those two, nothing would change. So this is a facility that we could use in S domain. You cannot use this facility in time domain. So pay attention. You're going to write less number of equations due to that serial connection elements. So let's start writing these node voltage equations. So the first thing that you've got to decide which Kirchhoff current law equations, which Kirchhoff law equations that you're going to use. There are two of them: Kirchhoff current law equation, Kirchhoff voltage law equation. So this is the name of the method is node voltage is named node voltage method. Just by looking at this name of this method, you can say that you're going to write Kirchhoff current law equations, because for nodes we wrote Kirchhoff current law equation. For meshes we write Kirchhoff voltage law equation. So since it is node, we're going to write Kirchhoff current law equations for this given circuit. So we've got three nodes, so we are going to write three equations. The first one is this one. According to passive sign convention, this independent source current reference is downwards, isn't it? Like that. Make it okay. So if we call it, this is IS, then coming out of the node, so IS is one of the current. The sign is positive because it's coming out of the node. So next current is this one. This current is coming out of the node. That's why the sign is going to be plus. Now, as you know, we in time domain for the resistive circuit, and in frequency domain, we wrote these node voltage equations step by step. First, current equations we wrote, we transferred currents to the voltages, and then we replaced the voltages with the element voltages, 3 steps. Now we will be writing this now in S domain directly, because we repeated it many times. So how I am going to write this directly? So I am going to write this current here, because I am writing Kirchhoff current law equation. This current, what this current is in terms of node voltages. So this current is the current of this resistor. So I can use this resistor definition relation and also use this resistor voltage. So if we are in the node voltage method, we can say that all the elements voltages can be written in terms of node voltages. Let me explain this once more here. Assume that this is element A. So if you know the node references, so you must know that, or if you don't have it, you've got to give these references. Once you give these references, so you're going to write the node voltage. So this element A has got 2 nodes. That means 2 node voltages related to this. So how I'm going to write this element voltage in terms of node voltages, we have already examined it, is VA is equal VD1 minus VD2. What is the rule? Is easy. Positive sign reference node voltage minus negative sign voltage reference node voltage. VD1 minus VD2. So this is the voltage of this element A. In this case here, the voltage of 10 ohm resistor is VD1 minus VD2. Divided by 10 gives you that current. So I was going to write this current in terms of node voltages. I can write it VD1 minus VD2 over 10. So this here, make it different color, this here is 10 ohm resistor voltage, and this altogether here is this resistor current, which is that I. So that is I. So since there are 2 elements connected to that node, so this is equal to 0. So I wrote Kirchhoff current law equation for the first node, node 1. So how are we going to write the equation for node 2? So we are going to write now Kirchhoff current law equation for this node. Since this current is coming out of node for this VD1, but for VD2 this is coming into the node, therefore the sign is going to be minus. So minus, we already write this current, so I'm going to repeat it, VD1 minus VD2 over 10, and sign is negative because it comes towards the node, this node. So plus this 20 ohm resistor current. Why it is plus? Because this is coming out of the node. So what is this resistor current in terms of node voltages? This resistor voltage is VD2 minus reference voltage. Reference voltage is equal 0, isn't it? That's ground. So that voltage is 0. VD2 minus 0, that means VD2 over 20 gives you this current. So VD2 20 is this current. So what about this current? This current is the inductor current. It's coming out of the node, so plus, it's going to be plus. Coming out of the node, plus sign. This element current, how I'm going to write it? I'm going to write this element voltage first, divided to 0, 1s impedance, gives me that current. So how I am going to write this inductor's voltage in terms of node voltages? VD2 minus VD3. VD2 minus VD3 over 0.1s. That's the impedance, 0.1s. That's the impedance. Now, you might say that how we wrote this, in this explanation, I used this voltage reference, but in here we've got current reference. So you're going to consider the passive sign convention, isn't it? So if the current reference is like that, so voltage reference should be like that. So VD2 minus VD3 as explained here. So that is the current. Now what is this? This is the inductor current. So we are writing Kirchhoff current law equation. Each term here is a current. So if you write a voltage here, if you write a power dimension term here, that means you made a fundamental mistake. Don't do that. So that is so we've got 3 elements connected to this node, so that's equal to 0. So let's come to the last node, node 3. So this inductor current coming towards this, so I am going to write minus in front of this IL current, minus VD2 minus VD3 over 0.1s is the inductor current for this node. So we've got to write this element current here. So in general, students, they do make a mistake when they face a dependent source like that. So what I advise you to do, before you try to write the Kirchhoff current law equation, write the definition relation of this element first. What is this element? This is a dependent source. Why it is dependent source? Because when it is circle, it is independent source. When it is diamond shape, it is a dependent source. So it is a dependent voltage source. Why is that? Because the voltage reference given in it. If the current reference given in it, it is a dependent current source. If the voltage reference given, then it is dependent voltage source. This dependent voltage source voltage depends on a current of another element. So that I is this here. So that I, make it a different color. That I here is that I here. This is another element. Now I can write the definition relation of this element. I am saying this is a current controlled voltage source. Current controlled voltage source. Since this is voltage source, voltage of this element is equal 5I. So that's 5I is not the impedance of this element. It is part of the definition relation. So you're going to write the definition relation like that. What is important in this definition relation is this. In this definition relation, we could see this element voltage only, not the current. So this element has a current, which is this, and this current depends on the circuit it is connected to. So this relation is always true. It doesn't depend on the other elements, whatever. It depends on the one of the element. It doesn't depend on the type of the circuit given to you. But this depends on the circuit. So that's critical. So keep this. and write it somewhere. Now let's come to our equation now. We are writing now Kirchhoff current law equation for this node. We wrote this current, which is this. So come to this element current now. As we said, that is this element. Can I transfer this current to element voltages and then the node voltages? I cannot, because in the definition relation, this current is not seen. So I will be writing this current as it is in here. I cannot use the definition relation to transfer this current to the node voltages. So it's going to be this current here. Leave it as it is. Don't write here VCCVS, because you are writing Kirchhoff current law equation. If you write VCCVS, you made a mistake, because current plus voltage, so are mixing up Kirchhoff current law equations and the voltage law equations. That is a fundamental mistake. Don't do it. So the last element that which is connected to that node is this equivalent impedance. So what is this impedance current? This current, since it is coming out of the node, it's going to be plus sign, and the current is this equivalent impedance voltage is equal VD3 minus reference node voltage, which is 0. So VD3 minus 0, which is the node voltage. So this impedance connected with VD3 and the reference node voltage, which is 0. Then VD3 over the impedance. The impedance is this 50 plus 10 to the power 4 over S. So this now maybe make a, so let's say icon. So this current here is this. Also you can say that this current, isn't it? This equivalent impedance current. So since there are three elements connected to this node 3 equal to 0. So we wrote Kirchhoff current law equations for all the nodes. Now what we are seeing here now, the unknowns are VD1, VD2, VD3, and this IS is unknown, and this ICCVS is another unknowns. And we've got three equations. Then it means that we've got to write two additional equations, supplementary equations. How I am going to write these supplementary equations? For those elements for which the definition relation has not been used before. For example, this element definition relation hasn't been used, and this element definition relation is also hasn't been used. That was a definition relation. I couldn't use that. I couldn't use the independent voltage source voltage definition relation, which is this. So we are going to write these two supplementary equations for this element and for this element. These are the elements of which definition relation have not been used. So what is the definition of this independent voltage source is given here. Let me to write it here again. VS S. This S comes from source. This is S domain S. Equal 10S over S squared plus 10 to the power 4. If you write this equation like this, this is the definition relation. It is not the supplementary equation. So you've got to transfer this to supplementary equation. How? Easy. We said all the elements voltages can be written in terms of node voltages, so you can transfer this voltage, independent voltage source voltage, to node voltage. How are you going to do it? Here you are. This is VD1 and the other terminal node voltage is 0, so this is equal to VD1. So this equation now is supplementary equation. This side is not. So what is the second supplementary equation? So I'm going to repeat here this. I will be using this definition relation that haven't been used before. That is VCCVS is equal 5I. So I can transfer each element voltages to node voltages. So I'm going to transfer this element voltage to node voltages. So this element, this element. So one terminal is VD3, the other terminal is the reference voltage. Reference voltage is 0, VD3 minus 0, VD3. So this is equal VD3 directly. Equal to 5I. So I've got to transfer this I, these unknowns, because I am trying to write 5 unknowns, 5 equations. New equations must have these unknowns only, not the other unknowns. So this is another unknown I here. So I've got to transfer this I to these unknowns. So how I'm going to do it is easy. So this current is a resistor current. So I can use the resistor definition relation and this resistor voltage in terms of node voltages. That means I can transfer it. So we already done it now. VD1 minus VD2 is this 10 ohm resistor voltage over 10 gives me this current here. So that current here is equal to this. So now look at this equation now. In this equation, I have got the unknowns that listed here. So therefore, this is the second supplementary equation. Now what we've got all together now, 1, 2, 3, 4, 5 equations and 5 unknowns. So I can find a unique solution. So you might say that 5 unknowns, 5 equations, it is better than how many elements we've got? 2, 3, 4, 5, 6, 7. So if you use the classical method, you're going to use 14 equations and 14 unknowns to solve that. Now we reduce it to 5 now. Still you might say that 5 equation, 5 unknown, still a big size. But you can reduce this size a bit further. How? Look at this equation here. Make it different color. In this equation, we've got IS as an unknown, and this unknown is only seen in this equation, not in the other equations. This means that I could use this equation only for the calculation of this current. So I will be using this later on, means after I found VD1, VD2, VD3, so I am going to use this equation in order to calculate IS. So I'm going to use it later on, leave it. So if you look, this node 3 equation here, and this current is only seen in this equation, not in the other equation. Therefore, this equation is useful in order to calculate this current after you found VD1, VD2, VD3 node voltages. So I will be using this equation later on. So leave it on side for a while. So what is left? This equation, this supplementary equation, and this supplementary equation. So 3 equations, 3 unknowns. But if you look at that, this VD1 is already known, isn't it? So this is known. That's source voltage. So if you replace D1 in here and in this equation, so that means you reduce your unknowns and equations to two equations, 2 unknowns. Unknowns are VD2, VD3, and equation is this one and this one after you replace that D1 with this. So you can calculate VD2, VD3, and you already calculate VD1. So if you know VD1, VD2, VD3, then you can calculate that IS. This is the one that we left on side. So you're going to use this. So you're going to use this equation now. After you calculate VD1, VD2 to VD3, you're going to use this equation in order to calculate this unknown. So that means you found all these unknown at that moment. So we could see it here. Here you are. VD1, VD2, VD3 we have calculated. That is the current controlled voltage source current from one of the equation as we have done it before. And this IS independent voltage source current. So at that stage now we found 5 unknowns here. 5 unknowns. These are VD1, VD2, VD3, and this 2. Now we are saying once we found all that, we can find now all the elements current and voltages. How are you going to find that? So here you are, VD through VD3, if you know that, so you can calculate that VL, inductor voltage. So if you use the definition relation of the inductor, then you can find the inductor current here, inductor voltage and current we found. You can write the VD1, VD2, if you know VD1, VD2, you can find the 10 ohm resistor voltage, use the definition relation, find the current. Similarly, you got to find the 20 ohm resistor voltage and current. In here, I see current, so that means, I'll show you this, maybe that helps. Yeah. So this current, so that means capacitor current and this 50 ohm resistor current are the same. This is written here. And so we already know VD3, that is the equivalent impedance voltage, isn't it? So if you divided this equivalent impedance, you're going to find this current. This equivalent impedance current is the same as the capacitor current and the 50 ohm resistor current since they are connected in serial. So I found these element currents. If you know the current of the capacitor, you can use the definition relation of the capacitor, find out the voltage, isn't it? So if you know the current of the resistor from node voltage, then you can find this resistor voltage by using definition relation. So I found this 50 ohm resistor current and voltage, and also find out the capacitor current and voltage. And I already found out this dependent source current here, and I know that dependent current controlled voltage source voltage is equal to VD3. So I found all the elements current and voltages. So that is the end of this video. Then let's stop here.